So now we are starting our second topic, which is coupled motion or pulleys. So pulleys is the most common aspect of coupled motion, but coupled motion is just two objects moving that are connected, where basically the motion of one object depends on the motion of the other object because they are connected. Now you could have more than two objects connected, but obviously you wouldn't have coupled motion if there's only one object because that's not a couple. So two objects move connected. We talked about this a little bit last time with like the parent pushing the baby in the stroller or the dog pulling a person on a skateboard, or a little bit with the wakeboarding. The most common aspect of this is pulleys, or application, I should say. So with a pulley, you can give yourself a mechanical advantage by reducing the force that you need to pull something compared to the amount that that thing weighs. But you do this at the sacrifice of speed. So if you add pulleys to a system, yes, it will reduce the force, but then it will have to increase the distance that you pull. Now, the book goes over lots of ways to calculate pulleys, like very mathematically. To me, the easiest way to do it is just to count the ropes. So if you want the like super detailed math explanation, chapter 12 in the book, but basically, we look at the pulling force. So the pulling force here is denoted by the green arrow. So pulling force P, and then we have mass M for the object. So this is a fixed pulley, which means that the pulley is mounted up on the ceiling. And they didn't really draw the ceiling in that picture, but here, pulley is mounted to the ceiling. Pulley does not move. So the person pulls, the mass rises. That's a fixed pulley. The second type is a movable pulley. So the string is fixed on the ceiling up here. And then the person pulls, the pulley is just hanging. So if the person let go of the pulley, everything would just collapse. Here the person's pulling up with force P. And that makes the pulley move and the mass moves. So that's a different type, movable pulley, because the pulley is moving. Compound is when you have multiple pulleys. So here we have one pulley fixed at the top. We have one pulley moving at the bottom. We have the mass. We have the force P. And this is a compound pulley set. And then the block and tackle is when the rope and the pulleys are sort of wrapped around each other. So you could wrap around and around as many times as you want. You could have multiple pulleys in there. This is used a lot in cranes to lift heavy loads, because you can get this in such a compact space, but still give yourself a huge mechanical advantage. So the cable on a crane will use this. That way the crane can lift a really heavy load without pulling the crane over or, damaging stuff. So this block and tackle, we have pulling force M here. We have the mass M, and then we have the rope kind of all wrapped around everything. Now, an assumption that we use here is that the rope is not flexible. Rope cannot stretch. So it can bend, but it can't stretch. Inextensible. And it's always in tension. So the rope cannot crumple and the rope cannot stretch. Just taut rope. Now, what I was saying as far as how to work the pulley problems, the easiest way is to count the ropes. So a typical pulley problem will ask you either for the mechanical advantage, which is going to be some ratio of pulling force to object force, or object speed to pulling speed. Now, we're still in particle kinematics, so we haven't added in forces yet. So I'm not going to ask you about forces, but I will ask you about speed. To solve, step 1, we count ropes on P. Then we count ropes pulling on mass. And then finally we compare. So we'll do an example of this fixed system now. So in this fixed system, we have one rope pulling on P. We have one rope here pulling on M. So there's one there for P, and here's one pulling up on M, equals 1 M. So this means that VP equals VM as far as speed goes. They're going in opposite directions. But as far, so really for direction, just like know the direction, is it going up or down? VP equals VM for the speed. So however fast or however far somebody pulls that P, that's the same distance or speed that M is going to move. So if VP equals VM, then we can also say that the change in distance for P equals change in distance for the mass. So the mass went up, the pulley went down. This is an absolute thing. So we're dealing with scalars here, not vectors. But if it asks for velocity, that's a vector. Okay, so basically if someone pulls on P 1 meter down, the mass goes 1 meter up. That's what this is saying. And then similarly, acceleration of P, not vector, just acceleration, equals acceleration of the mass. So when speed changes on P, it changes just the same amount on the mass. So the ratio here, the mechanical advantage that you're going to get here is going to be equal to VP over VM. And here it is a 1-to-1 because they're same. Now the movable pulley, we'll do that one next. So this one, we have one force pulling on P. And then how many ropes are pulling on M? Well, M is connected to this cable right here, and it's got 1, 2 ropes pulling up. So this means that P is only going to pull with half of the force that it takes to lift M. But we'll put the ropes down here. So we'll say that 1P equals, so now there's 2 ropes on M. So VP equals 2 VM, and the mechanical advantage VP over VM equals 2. So P had to pull twice as far to get M to move, and that's because M, like if P pulls 1 meter, then a half a meter is how far M is going to go up, because there's, from the 1 meter of P, we have a half a meter on the right side and a half a meter on the left side. It gets distributed like that. And so M's only going to go upwards a half a meter. Then on the compound, we've got 1 rope here on P. And then we've got 2 ropes here on M. So 1P equals 2M. That's exactly the same as what we had before. So VP equals 2VM, and VP over VM, mechanical advantage, is 2. The block and tackle is exactly the same as the other 2 we just did. So we have 1 rope here pulling on P. We have 1, 2 ropes pulling up on M. So VP over VM equals 2. So the easiest way with the pulley problems is literally just count the ropes, compare. So to solve these pulleys, we need to see, we're going to assume, okay, so this here is grounded. Here is the pulling force P. Here is the mass M. Now, a lot of these actually tell us the answer. So we're going to go ahead and prove the answer. How do they get that? So on here, I'll use a different color here. So on P, we have 1 rope. Now M here is connected to 2 different pulleys. So This one looks a little bit trickier because how do you know, do you count 2 ropes because it's connected up here to one pulley and up here to another pulley? Or do you count all 4 ropes that are pulling up? And the answer is that you count all 4 of those that are pulling up because these pulleys and the mass are moving together. And so this rope here that connects the mass to the pulleys is not changing length. So we can assume that is a rigid connection and that this is sort of all one group. So 1 rope, 2 ropes, 3 ropes, 4 ropes. Okay, so this is, I mean, you could almost think about this like this mass is a person and it's hanging from 2 rings. Okay, the person's arms are not going to change length. How many ropes are pulling up on that person? It's going to be the same as the ropes that are pulling up on the rings because the person is hanging from the rings and the person does not have any other ropes on him besides touching what is touching the rings. So here we have 1P equals 4M, VP equals 4VM, VP over VM equals 4. And in this situation, P and M are moving in the same direction. So they share velocity too and not just speed. If it asked you for velocity, then you have to include the sign, positive or negative, in this mechanical advantage. So just take note of that, whether it's on a homework or a test or something. Does it ask you for speed or does it ask you for velocity? Because if it asks for velocity, you need to know the direction. Okay, so this next one here, they're calling the double mariner. Boy, that one looks awful. Let's do this other one. V on Z. So this one is called a V on a Z because this right here, that rope is a Z. And then this rope here makes a V. So this is a situation where now we've got 2 different ropes. So we have to do 2 different equations. We can't just do one anymore. So we've got M here, we've got P here, and we cannot just straight up relate P to M because they're not on the same rope anymore. So we do one equation for each rope. And we need to look at where do the ropes connect? Well, those ropes connect on pulley 3. So I'm going to call pulley 3, we'll just call it C for connection point. So we'll do one equation for the red rope, one equation for the blue rope. So the red rope equation, this is going to relate the mass to C. So here we've got 1 rope for the red, 1 red rope is pulling on C. And then on this mass, we've got 1, 2, 3 pulling up on that mass. 3M equals C. 3VM equals BC. So here we have 1. P is just pulling on 1. P is not pulling on that other side. So P is pulling just on one side. And then on the blue rope, for C, we have 1 rope pulling up and 2 rope pulling up. So over here at P just sees 1 rope. P just sees this part. C, over here, this pulley, sees 2 ropes. So 1 P equals 2 C. VP equals 2 VC. And now we need to plug in this here. So now we get VP equals 2 times 3 VM. VP equals 6 VM. So then VP over VM equals 6. That's our mechanical advantage, 6-1. Let's do this V on V on V. Because this other 6-1, like that's very similar to the one that we just had. So the V on V on V. This one has 3 ropes. So now we've got 1 rope here, and then we've got 1 rope here, and then we've got another rope here. And we will assume that this is all grounded. So now we need an equation for each rope. So here we've got the mass M. Here we've got the pulling force P. So for the red equation, we look at the first pulley. We will call this P1, we'll call it A, and then P2, we'll call that B, and then P3, we'll call that C. So for the red equation, we look at M compared to ropes pulling up there. So based on this one, we have this rope here connected to this pulley, and then we have the 2 sides of it pulling up on the first pulley. So M and A, those 2 pulleys are immediately connected. So we know that M and A have the same speed. Okay, so writing this equation, we look at the intersection between the red rope and the black rope. To get that equation for the red rope, we have to know where the tip of it is moving. So that tip is point B. So we have 1 B, because there's 1 rope pulling down at B, equals 2 M, also equals 2A. Some people like to think of it that way. So 1 rope pulling on B equals 2 ropes pulling up on M. And then for the black rope is going to be just the same. We're looking at now here on B, we have 2 ropes pulling up on pulley B, and we have 1 rope pulling on C. And then now finally for the blue at point C, this is comparing to P. So P up here just has 1 rope on it. And then there's 2 ropes pulling up at pulley C. So let's put these all into one equation. We'll have P equals 2 times C, which is 2B, equals 4 times B, which is 2M, equals 8M. So P equals 8M, VP equals 8VM, our mechanical advantage, VP over VM equals 8. And in this situation as well, P and M are going in the same direction, so the velocity ratio would still be a positive 8.